Chapter 8 includes a lot of new topics for most people where we talk about polar numbers, polar coordinates, but it starts with a nice review for complex numbers. Well, review for some of you. If it's not a review, take your time working through this. If it is a review, make sure that you hang out with me to the end where we talk about dividing complex numbers and the powers of I, because that is still a review for most, or not a review, but still a new concept for most of us. Okay, complex numbers go back to our definition for I. Now, I is an imaginary number, but that does not mean it is useless in real applications. It's defined as our imaginary number because it was implied it was imaginary when it was first kind of discovered, when we figured out, okay, we need something to do with these square roots of a negative. But imaginary numbers are used in engineering and electricity and a lot of things with well, there's two big areas, engineering and electricity. Let's just go with that. So we define I, our imaginary number, as the square root of -1. If I square both sides of this, the squaring the square root cancels out so that I have I square equals -1. Now, we will never leave an I square. We always replace it in our problem with -1. Note that -I is also a square root of -1. Okay, a complex number. If A and B are real numbers, then any number in the form a plus bi is a complex number. In this complex number, A is the real part and B is the imaginary part because that's the coefficient for I. If A is 0, so the real part is 0 and all we have left is bi, the complex number is said to be pure imaginary. A pure imaginary number, such as, or a number such as 7 plus 2i with a not equal to 0 and b not equal to 0, is a non-real complex. Standard form is my form a plus bi. And then it shows us how our number system fits together. Now, you have two main boxes. You have real numbers and complex non-real numbers. A number cannot be both real and non-real at the same time. If we look over here, our non-real complex numbers are in the form a plus bi, where a is your real part, b is your imaginary part. Pure imaginary numbers have just that imaginary part. But there's some good examples of our imaginary number system. Over here, our real numbers are divided into rational or irrational. Your number can't be both rational and irrational at the same time. If it's irrational, it's square root of something or one of those irrational constants like pi. If it's rational, then we narrow it down, we walk our way through and we narrow it down. Integers, positive and negative, whole numbers, and 0. Whole numbers, which includes our counting numbers and 0, and then just our natural numbers are our counting numbers. Okay. Let me focus a little bit. When we have this expression, square root of -a, how do we deal with it? Well, for example, square root of -5, that's the square root of -1 times 5, which I could rewrite as square root -1 times square root 5. And by definition, square root of -1 is I. So this would be I square roots of 5. That's how we would simplify that. Sometimes we can simplify underneath a square root because we have a perfect square or because we have a factor that is a perfect square. Square root of -81, well, I know it's going to be imaginary. 81 is a perfect square. Square root of 81 is 9. So that comes out as let's do 9i. There we go. I stuttered and started to do it different ways. If I broke this down the way I did the previous one, it would look like this. -1 times 81. Square root of -1 is I. Square root of 81 is 9. D is also perfect square, imaginary number. These are all imaginary, but none of the rest of these are perfect squares. In fact, 55, 5 times 11 is 55. I can't do anything with that. It does not have a perfect square factor. So the only way to simplify that is to say I square roots of 55. Now notice that I put the I behind, except when I'm leaving it with a radical. And that's because if I put this I at the end, it would be kind of wiggly about whether or not that I was supposed to be underneath my radical. It's just best form to leave it out front, so it's very clear that it's I times the square root of 55. Here, 7 times 10 is 70. Neither one of those is a perfect square factor, so that just simplifies to I square root 70. But these two have perfect square factors. Now 98 is the same thing as 49 times 2. So that's a -1 times 49 times 2. Well, square root of -1 is I. Square root of 49 is 7. So I can bring out 7i. Can't do anything about square root 2. The square root of a -98 simplifies to be 7i square roots of 2. 49 times 2 is my 98. Square root of that -1 is I. Square root of 49 is 7. Can't simplify square root 2. What about this one? Well, 48 has a perfect square factor. 48 is actually 16 times 3. So I've got -1 times 16 times 3. Square root of -1 is I. Square root of 16 is 4. Can't simplify square root of 3. Alright, let's look at our next example. This time, instead of just given an expression, we're given equations, and we need to solve. Here I've got x squared equals -144. I'm thinking ahead. To solve for x, I need to take the square root of both sides. When I take the square root, I don't know if that variable should have been positive or negative, so I do a plus or minus there. X, the square root and the square cancel out to leave me with x, and I have plus or minus square root of a -144. Well, 12 squared is 144. It's negative, so it's going to be imaginary. So I've got plus or minus 12i. I have two roots here, two solutions, a positive 12i and a negative 12i. I need to solve for x. This one started out with the squared term equal to the constant. For this one, I have to move that 75 over. When I move it over, it becomes negative. I still need to take the square root to solve. Have to consider plus or minus. So x is going to be equal to plus or minus. Well, 75 is 25 times 3, and 25 is a perfect square, so I can bring out that, not 3, 25. Square root of 25 is 5. 5i square root 3. The 3 has to stay, can't simplify. So I have two imaginary roots there, 5i square root 3 and a -5i square root 3. This one's set up as a quadratic equation, and we're going to have complex solutions. It's quadratic because it's squared. I need to set it up in quadratic, my standard form for quadratic. So I'm going to move that constant over here. I want to factor if I can, but this is not factorable. If I have a quadratic equation that is not factorable, I need to solve using my quadratic formula. So I've got -b plus or minus square root b squared minus 4ac all over 2a. This should be, you should be comfortable with this from college algebra. So when I'm using my quadratic formula to solve, the opposite of b is going to be 2 plus or minus square root b squared -2 squared is going to be positive 4 minus 4 times a times c is a positive 5. I had to moved it over to get that sign correct for my value for c. 2a is 2 times 2. So I have 2 plus or minus square root of 4 minus, well, this is 10 times 4 is 40 over 4. Next step, 2 plus or minus square root of -36 over 4. Well, -36 is a perfect square. Square root of 36 is 6. It's going to be imaginary, though, because it's a -36. plus or minus 6i over 4, and I need to simplify this. Now I've got a couple of ways. We've talked about this before this semester. I can factor out this 2 in my numerator and look at it as 2 times 1 plus or minus 3i over 4, or I could say 2 over 4 plus or minus 6i over 4. Whichever way I do this, if I do this, I get 1 plus or minus 3i over 2. If I do this, I get 1/2 plus or minus 3/2i. That's the same solution. That is the same solution, either way. This is in my standard form for complex imaginary numbers, a plus or minus bi. This is really the best choice with how we want to write it. Operations on complex numbers. When I'm working with negative radicands, radicand is the value underneath the radical, I want to use this definition before using any of the other rules for radicals. Now what this tells me is I pull that I out from underneath my radical first. Before I do anything else, I pull out that I. I take care of the negative underneath the square root. Keeping that in mind, when I look at this, I say, oh look, these are both negative. Now I might be tempted to multiply that together underneath the square root symbol and write it as a single square root with a positive value. That would be wrong. I need to take care of the I first. This is I square root 21 times I square root 21. Well, I times I is I square. Square root 21 times square root 21 is square root 21 square. We never leave an I square. I square is equal to a -1. Square root of something squared is just that thing, so my result is a -21. If I had gone the other way, if I had said, oh, I can multiply that together and I've got negative times a negative is a positive, that would come out as a 21, positive 21, not a -21, that's wrong. Okay, let's look at this one. We're going to take care of that I first. So I've got I square root 5 times I square root 30. I times I is I squared. Underneath my radical, I can multiply those radicands together. 5 times 30 is 150. Perfect square factors. Well, 25 is a perfect square, and 25 goes into this 6 times, 6 quarters in $1.50. So I've got I squared is a negative. 25 times 6, square root 25 is 5. So -5 square roots of 6. Let's look at C. My temptation is to put this all underneath one radical, but if I do that, I will mess up. I've got to take care of the I first. Bring out that I. Well, anything over itself is 1. So now I can think of this as square root of 42 over 3. And 42 divided by 3 is 14. So I have a positive square root 14. Right here, same thing. I need to start by taking care of the I first. And then I can look at it as a single radical. 63 divided by 21 is 3. So I have I square roots of 3. Order matters as we are simplifying. Alright, we are flying right through. Let's see what we've got for example 5. Simplifying a quotient involving square root of a negative. We want to write this in standard form, a plus bi. The first thing I want to do is see if I can simplify my radical, and I can here. 75 is 25 times 3, and 25 is a perfect square. So my numerator is 15 minus 5i square root 3, and then I have that all over 5. Remember we said we can factor out my common factor in my numerator, or I can think about it splitting it apart. Either way, you're going to get the same result. When we simplify completely. For this one, again, I want to simplify this value. You may have to play with that a little bit to find your perfect square factor. 128 is actually 64 times 2, and 64 is 8 squared. So 128 is 64 times 2. So that is 8 square roots of 2. It was negative, so that comes out as an 8i square root 2. Negative 128, that's an 8i. Alright, so we've got negative 8 plus 8i square root 2 over 4. If I split that apart again, keeping my denominator of 4 there, that simplifies to a negative 2, and then I've got 2i square root 2. If you don't like splitting it apart, you really can. You can go in here and you can say, okay, well those have an 8 in common, right? But when I factor out that 8 here, then I can just reduce by 4, and that's going to leave me a 2 to multiply back in. So that I just really find that is the most effective way. Now when I'm adding and subtracting complex numbers, really all you need to remember is that you combine, you add or subtract those real parts, and then you add or subtract the imaginary parts. You're just combining like terms. You're just combining like terms. That's all you're doing. Looking to see what things you have that are alike and combining those things. So for A, for example here, I have 5 and negative 5. Those are real, and that adds to 0. Negative 4i and positive 8i, those are both imaginary, and that leaves me with a positive 4i. For this one, I am subtracting the second imaginary number, so I need to think about distributing that as a negative 1 inside. So I have negative 10 plus 7i minus 5 plus 3i. That takes care of those parentheses. And then I can go in and say, okay, my real part's here, negative 15. My imaginary part is a positive 10i, and I have a plus bi form. Let's do that for this one. Let's take care of, eliminate our parentheses. We need to distribute a negative in the second imaginary number. So we've got 8 minus 8i plus 2 plus 5i minus 10 plus 3i. Our real numbers, 8, 2, negative 10, that adds to 0. Our imaginary numbers, negative 8, plus 5, plus 3, that adds to 0 as well. So everything there adds to 0. Multiplying complex imaginary numbers, you are just foiling, okay? You're just going to FOIL. So we're not even going to walk through that. We're just going to remember that we're going to FOIL, and then we're going to do some examples. We have lots of examples here. I'm going to work down this first column, and then I'm going to give you answers for the second column so that you can go back and check your work and make sure you get the same answer. So let's work down the first column. Multiplying two binomials, they're complex imaginary numbers. We're just going to FOIL. First product, 5 times 2 is 10. Outside product gives me a negative 35i. Inside product gives me a positive 6i. Last product is a negative 21i squared. Well, right here, negative 35 and positive 6 is a negative 29i. So I have 10 minus 29i. Remember, we don't leave an I square ever. I square is equal to negative 1. So this is a negative 21 times a negative 1. That is plus 21. And now those are real numbers that I can combine together. So I've got 31 minus 29i as my result. You will never leave an I square in the answer for your problem. For the next one, I'm squaring a binomial. You can either write this out to FOIL it, or you can remember your pattern. My pattern for squaring a binomial, you square the first term, Multiply the two together times 2 because the outside and inside products would be the same. So that would be a negative 20i times 2 is a negative 40i. And then square this second term. Negative times negative is a positive 25i squared. Negative 5 times negative 5, I times I. Gives me a positive 25i squared, but that I squared, we never leave an I squared there. That's a negative 1. So that's 16 minus 40i minus 25. 16 minus 25 is a negative 9. So negative 9 minus 40i in a plus bi form. And then our last one here on this side, these are conjugates. They're the same values, just a different sign in the middle. Whenever I multiply conjugates, those outside and inside products add to 0, and it leaves me with difference of squares. My first product, 9 times 9 is 81. That would be a positive 72i. This is a negative 72i. Those add to 0. Negative times a positive. 8 times 8 is 64, so no, negative times a positive is a negative 64, and then I times I is I squared, but that I squared is negative 1. So that is 81 plus 64, which gives me 145. Now, anytime I have two complex imaginary numbers that are conjugates, my result is going to be real. That's how those work. Now, I'm going to give you just the answer to these three so that you can pause the video and practice working through those three processes. Two complex numbers that differ only in the sign of their imaginary parts are called complex conjugates. The product of a complex number and its conjugate is always a real number. Those are both complex conjugates. We use those to rationalize denominators with complex numbers. To find the quotient of two complex numbers, or excuse me, to find the quotient of two, no, that was right. To find the quotient of two complex numbers in standard form, we multiply the numerator and denominator by the complex conjugate of the denominator of the bottom. So we are going to practice that. I'm finding a quotient here. I've got this complex imaginary number in my denominator. I don't like that in my denominator. So I'm going to multiply by the conjugate of the denominator over itself, because anything times 1 is just another way to write that number, correct? Now, what happens here in my denominator, I'm going to be left with a real number. My numerator is not. My numerator, that's just two imaginary numbers, that are two complex imaginary numbers that I'm going to multiply together. I need to FOIL. 5 times 3 is 15. Outside product is a negative 5i. Inside product is a negative 15i. My last product is a positive 5i squared. Let's go ahead and simplify that numerator before we look at the denominator. Negative 5 and negative 15 is negative 20. So I've got 15 minus 20i, and this becomes a minus 5 because that I squared is a negative 1. So my numerator is actually 15 minus 5 is 10 minus 20i. That's my numerator. So we worked all the way down on our numerator. Let's look at our denominator now. 3 plus I, 3 minus I. 3 times 3 is 9. Outside and inside products add to 0. Positive and a negative is going to be minus I squared. Well, I squared is a negative 1. So that becomes 9 plus 1, which is 10 for my denominator. And then I want to simplify. 10 over 10 is just 1. Minus 20i over 10 is 2i. That's the result there. All right, for B, 15 divided by negative I multiply by a well-chosen one that looks like the conjugate of my denominator. Well, the conjugate of my denominator is just a positive I. So that gives me 15i over a negative I squared. I squared is negative 1. Negative times a negative is a positive. So I've just got 15i over 1. And then our last one is over a positive I. So my conjugate is a negative I. I'm going to do negative I over itself. It's my well-chosen one. So I have a negative 3i as my numerator, and a negative I square is my denominator. Well, negative times a negative 1 is a positive 1, so my numerator is a negative 3i just over 1. Okay. Hopefully, some of you have gone, oh, I remember that, or, ooh, that is something new. I don't remember that at all. This powers of I is new to a lot of us. So I want you to kind of walk through this. Now, we're going to look at working through our powers of I so that we get a pattern. And then once you know that pattern, you're going to use the pattern as we work through simplifying powers of I down here. This is the last thing that we're going to do for this section 8.1. Okay, anything to the first power is just itself. So I to the first is just I. And we know that I squared is the same thing as negative 1. Those are kind of our givens, right? Well, I cubed is the same thing as I squared times I, because if I'm multiplying the base, I add the exponent. And we just said that I squared is negative 1. So I cubed is the same thing as negative 1 times I, which would just be a negative I. I to the fourth would be I squared times I squared, because again, if you're multiplying the base, you add the exponent. And I squared, we know, is negative 1. A negative 1 times a negative 1 is a positive 1. Let's look at the next one. I to the fifth. Well, I can rewrite I to the fifth as I to the fourth times I. And I to the fourth we just figured out is 1 I. So 1 times I is just I. I to the sixth I can rewrite as I to the fifth times I, because 5 and 1 is 6. That's my exponent. I to the fifth we just found out was I. I times I is I squared, which is negative 1. I to the seventh, I could go I to the sixth times I, or I could do I to the fourth and I cubed. I to the fourth was 1. I cubed was negative I. 1 times negative I is negative I. I to the eighth would be, let's do I to the fourth times I to the fourth, because I to the fourth is 1. That's easy. 1 times 1 is 1. Now let's go through and let's look at this pattern. We've got I, negative I, oops, I, negative 1, negative I, 1. I, negative 1, negative I, 1. And so on, and so on, and so on. Powers of I are going to cycle through those same 4 outcomes. I, negative 1, negative I, positive 1. Since I to the fourth has the same multiplicative property as 1, I to the fourth is the same thing as 1, right there. I to the fourth is just 1. Also, any power of I with an exponent that is a multiple 4 is just 1. Right here, I to the 8th is just 1. So I to the 12th would just be 1, because I to the 12th would be the same thing as I to the 4th raised to the 3rd power, so that's just 1 cubed would just be 1. Right? Okay. So, how do we simplify the powers of I? Well, we are going to use that pattern. You'll notice that we've got positive exponents here, negative exponents here. We're going to do our 2 positive exponents first. Now, our base is going to be this I to the fourth is the same thing as 1. So we're going to see how many I to the fourths we can get out of this. Well, 4 times 8 is 32. So I to the 33 is I to the fourth raised to the 8th power times 1 more I. Because there's 32 and there's 1 more makes my 33. My exponent here is the same as that exponent 33. Now we said I to the fourth is just 1, so that's 1 to the 8th power times I. Well, 1 to the 8th power is just 1. 1 times I is I. Now do our other positive exponent next. I to the 15th. How do we get the exponent 15 in terms of 4? Well, 4 times 4 is 16. That doesn't help. Let's do 4 times 3 is 12. So I to the 4th 3 times is 12, which means this has to be times I cubed, because 4 times 3 is 12, plus 3 gives me an exponent of 15. I to the 4th is just 1. We've got 1 cubed, and we need to figure out what this would be, I cubed. I is just I squared was -1, I cubed is -I. If you can't remember that, you can break it down to be I squared times I. This I cube is I squared times I. 1 cubed is just 1. I squared is -1. So this simplifies to be -I. So when we have positive powers of I, we're just breaking it down into things that we know. If you can remember that I to the 4th is 1 and I squared is -1, that is usually all the work you really need. Okay, what if it's a negative exponent? If you have a negative exponent, you're going to multiply by 1 in the form of I to the 4th to get positive exponents. Now, what do I mean by this? Well, I to the 4th is just 1, correct? I to the 12th is just 1. I to the 8th is just 1. And anything times 1 is itself. So when I have I to the -3, if I multiply by I to the 4th, I'm just multiplying by 1. And anything times 1 is itself. Well, if I'm multiplying the base, what do I do to the exponents? Well, I add the exponents, right? So -3 plus 4 is 1. That would just be I. Let's do one that's a little bigger. So I want to multiply by some value of I to the 4th that's going to give me an exponent that is this positive. I know I'm going to be adding these exponents. So I to what exponent? Well, my multiples of 4. 4, 8, 12, 16, 20. Oh, I went too far. 16 and -14 is going to be a positive. So I'm going to do I to the 16 because I to the 16 is just I to the 4th 4 times. So that's just 1, which means I'm just multiplying by 1 here. And I chose I to the 16th because when I multiply the base, I add the exponents, and -14 plus 16 is a positive 2. And we know I squared is -1. All right, that is all of this first section in Chapter 8.